Okay, that's 2 minutes by my clock. So hello, everyone. Thank you for joining another IRENA online seminar. I'm James, and I'm a postdoctoral researcher at Keele University. I'm part of the CATEC Infra project working on capacity building, and I also look at explosive nuclear synthesis. And today, our speaker is Vishnu Varma, who is an expert in magnetic fields in core-collapse supernovae and their progenitors. He studied at Queen Mary's in London for his undergraduate degree, and then moved on to Monash University, where he studied for his PhD with Bernard Muller. I don't think there's I think that's enough of an introduction, so I'm going to mute myself and let you get on with it, Vishnu. Questions, anytime you want to ask a question, just raise your hand on the interface, and then we can take questions at any time. Vishnu's happy to do that, so I'll leave it up to you.
Yeah, good. Right. Thanks for the introduction, James. Also, yeah, I'll try and keep it the raised hands in mind, but if you can just sort of yell it out, James, when you see something, that'll be great.
Will do.
Yeah, thanks. Yeah, thanks everyone for joining. So maybe I'll just get sort of right into it, since James has already given me quite a nice introduction. So I'm just going to be talking to everyone about multidimensional modeling of magnetic fields and in supernovae and their progenitors. Yeah, so before I start, I always like to give a little bit of some caveats. So I will always say the word supernova, and when I do, I always mean core-collapse supernovae. I'm not going to talk about type 1As in any capacity. I know there's a lot of nuclear physicists who might be joining us, and I apologize, but I use CGS units. But I've given some nice conversions for the main units I'll be talking about in this talk. We use CGS units for historical reasons, even though we're talking about very massive things. So I'm just going to continue with that. Also, for the astrophysicists around, my work deals with really short timescales in astrophysical senses. So, as opposed to millions of years or even hundreds, in our simulations, we work in the seconds, or in the supernova case, the hundreds of milliseconds regime. And finally, I'm not a nuclear physicist. I haven't dealt with a whole lot of nuclear physics. I'm more of a fluid dynamicist, and I deal in these regimes, and I deal with the magnetic fields in them. But I'm going to try my best to highlight as much of the interesting nuclear physics that are occurring in these phenomena as I can. So just a bit of an overview of how the talk is going to go. I'm going to, since this should be a pretty broad audience, I'm going to give some a primer on core-collapse supernova theory, and then talk a little bit about the impact of progenitor models before I finally actually start talking about magnetic fields supernova, and then their progenitors, and then and when I start talking about magnetic fields in supernova and their progenitors, I'm basically going to start talking about actual results and publications that I have. So to begin with, the question is, how do core-collapse supernova explode? So to start with, we really need to go back a little bit to the case of the cell evolution of massive stars. So this is obviously not to scale, but really in a massive star, it starts with a burning of hydrogen in the core, and then helium, and it starts slowly, as it evolves, it starts burning heavier and heavier nuclei in the core, and eventually also in envelope layers, before finally, when its iron core gets massive enough, it starts collapse. So let's see. Yeah, so the collapse of the core really happens due to a couple process, largely in the beginning by photodisintegration of the iron nuclei, because you have incredibly high densities and temperatures, and as they collapse, and once it's collapsed to a much higher density, which somewhere around 10 to 11 grams per cubic centimeter, we start getting very high rates of electron captures. So, and once that happens, you basically accelerate the collapse until you hit nuclear densities. So once you hit nuclear densities, the collapse is halted, and you just release a reverse shock wave. Basically, is launched from the core outwards. So I think classically, the simple early picture of the core collapse supernova is just this: the core collapses, a shockwave is launched, and then the shockwave just carries on through, and that becomes our core collapse supernova. Unfortunately, this isn't really the case. As the shock starts moving outwards, it slows down due to a couple of different processes. One, the shockwave starts photodisintegrating as well, losing quite a bit of energy, but also because of the collapse of the star, you have quite a bit of ram pressure from material outside of the shock that's interacting with the shock, slowing that down. So generally, this shock tends to stall around about 200 kilometers or so. So really, the question of core collapse supernova for the longest time has been, well, now we have a stall shock. What mechanism continues to drive the supernova outwards into a classic core collapse supernova that we can see that breaks through the outer layers of the star? Well, the story that we get told that I'm not sure is entirely true is that when working on the simulation, one of the big names of the field, Jim Wilson, I think in Lawrence Livermore laboratories, I can't exactly remember, saw these stagnations, and everyone thought that, well, this is just a mistake. And one day he accidentally left the simulation running overnight and came back and saw that the star had exploded. So what we the base starting from there and onwards, what has been thought is that what we need is really some time for neutrino energy to build up behind the shock to then continue to carry its energy and launch the supernova shockwave. So I'm going to talk a bit about the actual physical mechanism that happens here. So you can see in this picture, we have, once the collapse happens, you form a neutron star. And because of the very high temperatures, you start from the surface of a neutron star, you're having a lot of cooling via neutrinos. So neutrinos are being released, but then there are also a bunch of interactions that are happening when the neutrinos are interacting with the material and heating them up. Neutrino heating and cooling don't fall off at the same rate. You have heating of neutrinos that scale with radius to the -2, and the cooling scales with radius to the -6. So you can imagine that once these neutrinos are interacting, there gets to be a point because of the difference in fall-off rate where there is a balance between the cooling and heating rates. After which, because the heating is falling off a bit less, there's a region where heating via neutrinos becomes the dominant. So this radius where the balance happens is what we call the gain radius, which is labeled over here. And basically, the entire region from the gain radius until the actual shock wave is what we call the gain region. The gain region is, I'm sort of gonna refer to it a couple of times again throughout this talk, because really that's where a lot of the interesting and important physics happens that re-energizes the shock really and continues the core collapse supernova mechanism. So now we know that there is a heating process that's happening behind the shock. What leads to this runaway expansion of the supernova? We can think of this with these two timescales. One is this advective timescale, where material that's coming from above the shock is being accreted into this gain region. And so the advective time is the amount of time that's spent by the accreted material inside the gain region. And then you have this heating timescale. So how long it takes for, material inside this gain region to be unbound by the neutrino heating. We tend to use this parameter to see when a runaway expansion happens. So basically the advective timescale over the heating timescale, once it gets above 1, basically saying that you have the heating timescale becomes incredibly quite a bit smaller than advective timescale. You start unbinding all the material within the gain region. You can imagine that means that you start expanding your shock. But as you expand the shock, the material inside it is at a larger radius and is less bound by gravitational forces. So the heating is actually, it gets easier for the neutrino heating to unbind more and more material, which causes a runaway explosion. So this mechanism is what we call the neutrino-driven mechanism, or sometimes also called the delayed neutrino-driven mechanism. And the delayed really because as opposed to a direct shock, you have a pause for several hundred milliseconds, which is long enough to change things in this regime. Yeah, so the general mechanism is that you have enough neutrino energy that that drives the explosion, and you have enough energy basically from binding and gravitational binding energy in the material, which gives you about 10 to the 51 ergs of energy, which is canonically what we see in core collapse supernova. Unfortunately, it isn't really so straightforward. Early core collapse supernova simulations were done in 1D, meaning complete spherical symmetry. And with my story from Jim Wilson, like these supernova only really exploded in spherical symmetry for the lowest high mass stars, meaning around the 8 to 10 solar mass range. Anything higher than that in spherical symmetry, we never saw an explosion. It took a couple of years, but we realized that what really needed was multidimensional effects. So once you have multidimensional effects and instabilities that fall behind the shock, you can then have much more efficient heating of the material and more efficient transfer of energy to the shock that then launches the supernova. So yeah, I'm going to move and talk about the impact of progenitor models. And to do that, I need to talk a little bit about how progenitor models are classically used in the core collapse supernova simulations. So as I talked about before, the progenitors of core collapse supernova are just the final phases of massive stars. These are stars that evolved over millions of years to get to the point where the cores are collapsing. So in order to do that, we tend to take 1D stellar evolution models that have run the entire evolution of the star and map them into our, let's say right now, our 3D codes, and then allow for a breaking of symmetry and then let them explode. This, as far as we know, this gives quite a reasonable structure for the actual core of the star that explodes. But quite recently, so it started being explored in 2015, first by Couch et al. And then Muller et al. In 2016. They started exploring multidimensional progenitors and then running them to core collapse. And what they found is that these asymmetries prior to core collapse can actually impact the core collapse supernova mechanism. So purely having a spherically symmetrical stellar model isn't necessarily a realistic initial condition. So yeah, so this was investigated more. So I think we can look at, so this model over here on the left was Bernard Muller, so my PhD supervisor, was the first person to do full 3D simulation of the final phases of burning, of oxygen shell burning of a massive star just prior to core collapse. And so he ran that to explosion. And in particular, so if you look at the plot on the right, I tried to write what they meant, but in particular, did some comparative studies. So this red line here, so the 3 lines refer to the maximum, the average, and the minimum shock radius, really just because the shocks aren't spherically symmetric. So this is just taking account the asymmetries. The red line is using this 3D progenitor structure that's mapped into to core collapse code. The blue line is using the 1D progenitor model, and this black line is using the black line is the 1D progenitor model. The blue line is using another 3D progenitor model, but where the Mach numbers of the inflow is reduced quite significantly. And as you can see, what happens is that using just the 1D progenitor model, the supernova doesn't explode, or at least within this time scale, supernova seems to fail to explode. Whereas just by having this additional multidimensional structure prior to core collapse, you do get an explosion. And also, you can see the the impact of Mach numbers. So really higher Mach numbers tend to lead to more rapid and often even more energetic explosions. So everything this year, so from their investigations, they found that really large scale convective flows, so things that have spherical harmonics of the order of L = 4 or less, tend to be the most have the most impact on the actual core collapse supernova mechanism, and also high Mach numbers, somewhere above 0.1, 0.1 of the inflows tend to have a pretty significant impact on the core collapse mechanism. So this entire mechanism where you have like perturbations prior to the large scale perturbation prior to the core collapse is something it's currently known as the perturbation aided supernova mechanism. The idea here is that, like I was talking before, in the gain region, you have multidimensional effects can really improve the amount of energy that's absorbed to the shock and launch the explosion. Having infalling material that is asymmetric can interact with the shock and perturb it just because of asymmetric ram pressure fluctuations, and that can cause higher turbulent kinetic energies inside the gain region, which again can speed up the process of heating in these regions. So from the title of the talk, you know that what I'm really interested in is magnetic fields. So what about the magnetic fields? So far, just talked about this classical mechanism. Nothing's been added. So magnetic. So in the field of supernovae, generally what's been assumed is that magnetic fields are dynamically very weak. And by weak, what we mean is that it's much weaker than the kinetic energies. And because we think that they're much weaker than, the magnetic energies are much weaker than kinetic energies, it's generally assumed that they're going to be dynamically irrelevant once we have the actual supernova mechanism. So really it isn't or wasn't a bad assumption to try and ignore them early on. The idea was the only times that they become relevant are for very rare cases of core collapse supernova, which we refer to as hypernovae, which have explosion energies of 10 to the 52 ergs, so something around an order of magnitude larger than the classical core collapse supernova. So the mechanism here basically assumes that you have incredibly strong initial magnetic fields and incredibly rapid rotation, particularly in the neutron star. And once you have this, rapid rotation about the order of 1 millisecond periods, you have enough energy of the order of 10 to the 52 ergs to actually drive the supernova. And really, one of the best ways to transport this energy is through very strong magnetic fields. And so with this rapid rotation and strong magnetic fields, you can achieve basically these collimated jets of energy and get these nice hypernova explosions. Really, this is so in the field, this is what is assumed. In the normal core collapse supernovae, we have, we don't need magnetic fields, and we only use magnetic fields when they're very strong with very rapid rotations, but those are only hypernovae progenitors. Right, not changing slides. So one thing that Bernard and I looked at in early 2020 was, well, this is what said, but no one's really investigated whether weak magnetic fields do anything, especially in the 3D case. So what we did was we added very weak magnetic fields to the supernova progenitor. Weak meaning we actually made it a point to choose a magnetic field strength that we thought wouldn't amplify to a point where it would be equivalent to the kinetic energies. And we ran 2 supernova explosions. Really, this hydro case of this red line is a progenitor that had been run before and had been known that failed to explode, but it sort of was marginal, close to actually exploding. So you can see this from this time scale parameter that I talked about earlier. Once you get to 1, you kind of know that you're going to get above 1, you're going to get runaway explosion. So this model sort of touches the line, gets close to explosion. So that's part of why we chose this model. And we just added these very weak magnetic fields, somewhere of the order, well, weak in in these terms, somewhere of the order of 10 to the 6 Gauss in the core. And as you can see, what happens is that that we do achieve supernova explosion just by having these very weak magnetic fields. What we found happens is that in the gain region, just by proxy of having magnetic fields, you can see that this time scale start to decrease initially, and what we think happens is that the shell contracts a little bit, and convective motions inside the gain region sort of amplify, and they increase they start to amplify the magnetic fields inside the gain region quite significantly, up to about 50% of equipartition. So still quite a bit lower than the kinetic energies. But what this does is, what it seems that it does is that it increases the convective efficiency. So the efficiency of material being heated heating efficiency of the material in the gain region, which then launches the supernova shock. So I've sort of put this slide in to take a little bit of a break. So I think for those who are not familiar with the supernova theory, I feel like I've given a lot of information, basically. But the basic gist of things is that realistic progenitors and gain region dynamics are really important for shock revival. And even weak magnetic fields can play a role in the supernova mechanism, although it is a pretty subsidiary role. So well, now we know that magnetic fields can do something, even weak magnetic fields in the core collapse supernova. The question then becomes, what do real magnetic fields in stars look like? In particular, of course, what do realistic magnetic fields look like in these final states of very massive stars in the cores? As this is really where the dynamics matter for the core collapse supernova mechanism. So to answer that, we have to start with the question of where do magnetic fields come from in stars? There are really two theories behind this. One is called the fossil fuel hypothesis, where as we say that magnetic fields were already present from some early evolutionary process, maybe in the formation process or something else of the star, and that some stable equilibrium of the magnetic fields kind of forms, and they are relatively stable, and they only diffuse away in timescales that are much longer than the timescale of the evolution of the star. So that's one possibility. The other one is that we have dynamo effects. So dynamo. So I show this of our sun. This is a dynamo of our sun, where you have a coupling of rotation, and this is differential rotation along with convective motions on the surface, which then continuously generate magnetic fields. So that's two general ways, but how are they treated in stellar evolution models? Because like I mentioned, that's generally what we use as our initial conditions for core collapse supernovae. The most widely used method in supernova, in stellar evolution, is to really assume that sort of ignore what's happening in the convection zone, but to really say that the main dynamical role of magnetic fields in stellar evolution is that magnetic fields are very efficient at transporting angular momentum, and hence they increase mass loss, induce magnetic braking, and things like that. So it doesn't have doesn't necessarily have any other important dynamical effect. The most widely used method is this Taylor-Sprout dynamo. Came up with the Sprout in 2002. Basically, the idea here is that since we could see magnetic fields on the surface of massive stars, even when they're radiative, the idea was that we could have a different dynamo mechanism without convection that happens just in the radiative zones due to this Taylor instabilities that form and the coupling with that and rotation. There have been some attempts to understand influence in 1D convection zones, but as far as I've seen, that hasn't really taken off. It hasn't really been used in the wider community. So really a lot, and most of what we know of magnetoconvection in stars is from solar physics. And while they've done some genuinely amazing work, it's really hard to extrapolate that. Magnetic fields or magnetic convection is extremely nonlinear. So it's hard to take what they've done and say that this will affect the core burning process in massive stars in a similar way. There's also the question of what would a realistic magnetic field strength be in this phase of star, or what realistic magnetic geometries would be because of magnetoconvection in the star. So this sort of led to one of the big projects that I did during my PhD, which was doing some magnetic shell convection. So this was so what we did was we ran a 3D simulation of an 18 solar mass star. So this was taken from Kepler, so stellar evolution code. Stellar evolution code, and we mapped it into 3D into our coconut FMT code. What we did was we excised in order to reduce computation, we excised the mass in the core region and treated it as a point mass. And like I said, we wanted to understand what realistic magnetic field strengths and geometries would be in this field, and we really didn't know what that would look like. So what we did was we took this oxygen shell burning phase and we implemented what we thought was a relatively weak magnetic field strength, so about 10 to the 8 Gauss, and just set it to be homogeneous, so equal all around, but in the polar directions, just to allow these convective motions to basically amplify and create something more natural. And then we also ran a pure hydrodynamic model for comparison. So what did we find? So in terms of magnetic field strength, by the end of a simulation, so it's about 700 seconds. I think we ran this for about 17 convective turnover times. So things were getting quite is relatively long for this time scale. We're getting that on average, we're approaching 10 to the 10 to 10 to the 11 Gauss in the oxygen shell. Which is quite high. So especially since I've mentioned before that we, for our previous magnetic supernova model, we used something of the order of 10 to the 6, and that was in the core. So this is already quite strong. The other thing we're going to look at was geometry. So even in the magnetorotational mechanism that we're talking about, or in our previous magnetic supernova mechanism, what we tend to use is the classic just magnetic dipole. And so we wanted to compare the field strength that we got to a dipole. So this red line is the dipole contribution of the total magnetic field, well, in this case, just the radiomagnetic field. And what we find is that the dipole contribution is about an order of magnitude smaller than the actual, the total magnetic field at any given point in this oxygen shell. So that's quite interesting. It basically tells us that we have quite a large contribution in these convective zones of non-dipolar magnetic fields. So more toroidal magnetic fields, we'd say. You might notice that this very large spike in dipole contributions over here, that's really just an artifact of the inner boundary conditions of the magnetic field, which we set to just continue being homogeneous. And so while we were looking for differences in the what realistic strength and geometries would be like, we found something else that was quite interesting in terms of the convection. So over here, I'm showing a plot of different stresses. So I think this over here. The black lines are kinetic stresses, and the red lines are magnetic stresses. Already just from, just from looking at this, you can see that, well, on average, you can see that the kinetic stresses are about an order of magnitude higher than magnetic stresses. So you can tell that, the initial assumption that supernova theorists made, that magnetic fields would be irrelevant in this regime because they are really weak, did make sense, right? You get an order of magnitude lower magnetic field strength. What we found that was quite interesting is at this point over here, which it's a bit 2.3 or so solar masses, we have sort of what I like to call sort of a quasi-equipartition. We get a quasi-equipartition between the angular magnetic stress components and the radial kinetic stress components. And what's really happening here is this point where this equipartition is happening is the upper boundary of our oxygen shell convection. And this isn't a full equipartition, but even this weak suppression is happening. Well, this weak equipartition is happening. What we think is because of a current sheet basically forming at the upper boundary of the convective shell, really because the convective plumes are pushing magnetic fields and compressing them against the upper boundaries and also on the lower boundaries, which is causing a bit of a peak in magnetic field strength on either ends of this boundary. So what does that do in a dynamical sense? So there are a couple of plots here, but really what I'm trying to show here is that just by having this quasi-equipartition and stronger magnetic field strengths at the upper boundary, the magnetic fields are very weakly suppressing mass entrainment into the oxygen shell. We can see this in a couple of different ways here. So the top left plot is showing the radius. So in purple, we have the purely hydrodynamic version that we're comparing with the black line, which is the magnetic version. And you can see that, over time, and this is just a couple hundred seconds, right? That the size of the hydrodynamic oxygen shell is growing larger than the magnetic model. In terms of oxygen shell mass, the hydrodynamic model is entraining much more new fuel to burn, so new oxygen material compared to the magnetic model. And because of that, just because of that, you can see that there's a slight increase in energy generation from the hydrodynamic model compared to the magnetic model. So we think that, I think that's very interesting because this is just happening over a very small time scale, over 700 seconds. Obviously, like I said, with these things in magnetic fields, it's very difficult to really extrapolate how this is going to affect different regimes and different parts of different mass stars and different parts of the evolution. But this is, in my opinion, quite an interesting find, because if this does have a larger impact on all convective boundaries, this suppression of convective boundary mixing could really have an impact on overall long-term stellar evolution, and as well as the observable abundances that we see on the surface of stars. Really, what we need is, because in 3D we're very much limited to the timescales that we can run these evolutions. So what we would need going forward would be some sort of 1D prescription to be able to evolve these stars over its entire lifetime to really understand the impact on the nucleosynthesis. I've also put this in to say that, well, this could also have an observable impact for core collapse supernovae. There's some work done by Anders Ekstrand that has shown that if supernovae that have particularly high nickel to iron ratios that are observable, probably you are able to sort of constrain how much silicon burning has occurred in the star during its evolution, based on the nickel and iron ratios. So, if we had a baseline, we probably could tell if mass is actually being, well, entrainment is being suppressed because you would, over a long period, have a much lower amount of silicon burning in the star. So really the big takeaways here is that magnetic fields can affect convective boundary entrainment, but in terms of what we want from core collapse supernova, we can see that in the oxygen shell convective regions, we can get fields of 10 to the 10, 10 to the 11 Gauss, but for our non-rotating case, this is still not above equipartition. This sort of leads to our next project on, we started with a very weakly magnetized supernova model, and we found out that, well, we can get quite strong magnetic fields in these cases. So what happens when you implement, very strongly magnetized models without the rapid rotation that you get from the magnetorotational supernova model? So we used a progenitor from Schneider 2019 and 2020. So in 2019, Fabian Schneider ran these stellar merger simulations, where it's a merger between, I believe, an A8 and 9 solar mass star. And what he found was, you can significantly amplify magnetic fields in these stars. So we took this progenitor, which he ran to merger, but then in his 2020 paper, they used a MESA model to continue running this progenitor up to core collapse. So we took that progenitor model that was magnetic, and we added our own basically magnetic field conditions. In Fabian's merger product paper, what they found was that they created quite a strong twisted torus magnetic field structure. And the fact that in our shell convection project, we also found, well, not a twisted torus necessarily, but quite strong toroidal components to the magnetic field, we decided to implement a twisted torus magnetic field geometry to our supernova models. We ran two models, one that we considered the weak model, which was again at the core strength of 10 to the 6 Gauss, and one that was strong magnetic field strength of 10 to the 12 Gauss. And really what we did was since we knew that it was pretty realistic to have an oxygen shell region of about 10 to the 10, 10 to the 11 Gauss, we extrapolated what the central magnetic field strength would be from there, which gave us about 10 to the 12 Gauss. So again, this is this was originally a very, very slowly rotating progenitor, so somewhere around 2.2 to 10 to the minus 8 radians per second in the final phases where it collapses. So for simplicity, we just modeled this as a non-rotating star. So what did we get? What we found is that, well, as you can see over here, for our strongly magnetized model, we get very high explosion energies, but not only that, it happens at a very fast time scale. So I guess, why is this important? So in 2019, there's a paper by Murphy et al. That did a comparison between observed and simulated 3D supernova models. And what they found was that on average, a lot of our simulated models were a bit too weak compared to observed models. I will say that over the years, since this paper, there have been more and more models that 3D models that have become closer to canonically observed supernova models. So that's pretty good. But even though there are models that get to this 10 to the 51 regime, like ours has done so, by including these strong and what we consider realistic magnetic fields, we're getting to canonical magnetic explosion energies incredibly fast, possibly faster model, but I'm not 100% sure of that. So the interesting part about this is that naively, the first assumption you'd make, and the first assumption that I made, was that, well, compared to the weak weakly magnetized model where the magnetic field is playing a subsidiary role, this is probably having a much more direct impact. I think I would have expected that having a strong magnetic field might have meant that you would amplify the magnetic field so much that it reaches super equipetition, and it might be you might have magnetic pressures that are actually driving the supernova shock wave. But what we find is that that's actually not the case, and magnetic fields still play a subsidiary role even for this very strongly magnetized case. So I have a couple plots over here that it's trying to give you the picture. On the left, I'm just showing the fluxes, the energy fluxes of the magnetic field. So really you can just focus on the black lines. The solid black line is showing the total energy flux at, I think, about 0.2 seconds after bounce. And this dotted line is showing just the fluxes without the magnetic components. So there clearly is a contribution from the magnetic fields over here, but as you can see further on, it really isn't the significant contribution. The significant contribution of this shock propulsion is from the hydrodynamics. Just the pure hydrodynamics without the magnetic fields. So what did we find was, well, one of the very interesting things we found from this model is that by implementing very strong magnetic fields, the model effectively started behaving like a perturbation-aided supernova mechanism that I talked about before, where we use more realistic progenitor models with multidimensional asymmetries. You can see this from these ram pressure fluctuations. So these are plots of ram pressure fluctuations at 200 kilometers, and this is going from 0.01 seconds up to here 0.09 seconds just before the shock actually interacts, it actually hits 200 kilometers. And you can see that we're getting this very strong L = 1 mode, and like I mentioned before, having this very large, very large scale perturbations really does help the explosion mechanism. You might ask, well, why are we getting such a strong sort of dipolar asymmetry? I'm not 100% sure. We'll try looking at this. It's a bit hard to disentangle. What I think might be happening here is that having a very strong toroidal component may be causing some asymmetry on either sides of the equator, but I couldn't say for absolute certainty. So I talked about the fact that this is an incredibly fast rate of getting to a high explosion energy, and why is this important? So there are a couple works that have been done specifically by Saito et al. 2022 and Sawada and Maeda 2019, which have run mostly 1D supernova models to try and constrain the nickel abundances. And what both of them have found is that really, if you have explosion energies that take too long to grow, then you end up not having nickel abundances that are consistent with observed values. So in particular, Sawada and Maeda really say that you need growth timescales of less than 250 milliseconds, and by growth timescales they mean from core collapse to reaching 10 to the 51 ergs. It's about 250 milliseconds, and Saito et al. Finds similarly, but for like constraining it to about 300 milliseconds. And they're saying that's what you need to really achieve observable effects. And I think we are getting there. We are definitely not getting to this 50 milliseconds time scale that Sawada and Maeda say is the best match, but we seem to be getting the 10 to 51 ergs below these 250 milliseconds. I think this is sort of an exciting thing to show, particularly because while a lot more hydrodynamic supernova models are achieving these 10 to the 51 ergs and higher, the majority of them take about 1,000 milliseconds, so the order of seconds of slow growth to eventually get to this canonical values. Another very important thing, well, very interesting thing that we found is in the magnetic field strength of the neutron stars that form. So over here, I have density and magnetic field strength of the actual star, and we choose a density of about 10 to the 11 Gauss as our choice of where we'd say that the proto-neutron star is, or where the neutron star surface forms. And what we find is, so with the solid lines, I'm showing the strong magnetic field case, that we're getting magnetar field strengths. And that seems quite reasonable. We're started with a very strong magnetic field strength, and it's basically maintained there. But even for the very weak magnetic field case, we started with 10 to the 6 Gauss in the center. And in 300 milliseconds, we've actually amplified this magnetic fields to a magnetar field strength. It's very interesting, it seems to suggest that are we going to be overproducing magnetars? I think it's also particularly interesting because there's another group, Matsumoto et al., who have also recently been working on a similar problem, and in particular Matsumoto et al. 2022, the paper is currently on the archive as well. They have run 2 models, 10 to the 12 and 10 to the 10 Gauss models, and they also seem to achieve magnetar strength proto-neutron stars for both of those models. So it seems like we're overproducing magnetars, but I'm sort of skeptical about that, partly because, again, we are dealing in the regimes of hundreds of milliseconds, and there's a lot more dynamics to happen. We don't really know. We need much longer simulations of what's happening in and around these magnetars to know how they will actually appear once they become visible. It is a distinct possibility that the accretion that happens post the explosion onto the neutron star might eventually just bury a lot of the magnetic fields that make the observable magnetic fields much, much weaker than what they are at the moment. Another thing that we see is that compared to the Matsumoto et al. Papers, their explosion energies don't seem to be as high, and their shock revival isn't as quick as we do, even though they're using relatively similar magnetic field strengths. So it's hard to tell whether our model is exciting or it's just a bit of a coincidence that we got such exciting results. But one reason I could think of that might be a big difference between our models really is the magnetic field geometry, where we use the twisted torus field, they use the classical dipole. But I think really what we need to do is to have more models where we're testing the effects of these different magnetic field geometries to truly understand whether these have that big of an impact or not. Yeah, I think I've hit about 48 minutes. Thank you. Happy to take any questions.
Thanks, Vishnu. That was a great talk. Do we have any questions from anyone? Adam Griffiths, do you want to ask your question?
Yeah, hi. Thanks for the talk. It was really interesting. I was just wondering about when you were talking about the magnetic fields in the oxygen burning show. How long before collapse were the simulations you were doing? I mean, I don't know if that's important or not, or if it's just a generic, oxygen burning happening, or.
Yeah, that's a good question. So I kind of showed like a model from 2016 of Bernard's progenitor model, and so this is actually started like just a couple hundred seconds, maybe like 500 seconds before collapse, but we have chosen it's basically less realistic. So this is the same model that Bernard used in his 2016 paper for a purely hydrodynamic model. What he did was, because during this phase of evolution, the core is already starting to contract, and so they basically use the prescription in the inner boundary condition, because we're excising it to basically contract in to follow the Kepler-Stellar evolution code and how that's contracting, and that's allowing for the sort of infall velocities prior to core collapse. We're using the same initial model, but we're doing it a bit differently. We're basically fixed the boundaries, so it's very much it's hundreds of seconds and to collapse. But because we fix the boundaries and we don't contract it in any way, we've sort of run it for longer than that is necessarily realistic. A big reason for that was because we didn't know beforehand what constituted real magnetic fields and magnetic field geometry. It was difficult to figure out how to decide on what the boundary conditions of the magnetic fields should have been if we were trying to contract the core, because that could have made quite a bit of a difference, since while you're contracting, the magnetic fields should have been amplified as well.
Okay, yeah, that makes sense. And so is there any difference then between looking at this in an oxygen burning shell at this stage of evolution and going back to a carbon burning shell much before collapse?
Yeah, I mean, I think that's will probably be fun and very interesting to do, and I would like to. So in this case, we can say that, well, the reason we chose this was because it's just before collapse, right? And we can sort of extrapolate that into what's going to happen in the actual core collapse supernova itself. Doing it for the other shells, I think, will be probably working backwards towards the shells and larger cells would definitely be a lot better in terms of understanding the cell evolution and stuff of it. But they tend to just be larger shells, and it's more expensive and harder to resolve. The convective turnover timescales will be much larger and all of that. So this was sort of, I guess, the easiest first step. But everything else was something that I would like to do.
Yeah, okay. Thanks a lot.
No worries. Thanks.
Do we have any other questions from anyone? Okay, I've got a quick question. So you mentioned at the end with the magnetar resulting from this even the weak magnetic field. So, and you said there might be a problem with overproduction. Like how significant a problem do you expect this to be, right? Like what's the difference in the predicted from this versus the observations?
Great question. I don't remember off the top of my head what the percentage of magnetars would be compared to just standard pulsars or something, but not a lot, right? There shouldn't be a lot, but I guess like looking at this, I think if you like the fact that we are starting with something like 10 to the 6 Gauss in the center, which is incredibly weak, but that's getting up to magnetar field strengths, is basically saying that, well, every star is going to be a magnetar. Every core collapse is going to be a magnetar. So that's the level of overproduction if there isn't some other mechanism that's going to bury the fields, or if there's going to be there needs to be some sort of severe magnetic reconnection that's happening, or something like that that's going to kill off most of the magnetic fields. I guess the other possibility is that I haven't really looked into the geometry of things, but we'll have to wait continue a bit longer. Other possibility is that in a lot of the magnetars we're assuming just a pure dipole, and that's how the magnetic fields are done, and that's how energy is being lost. It could just be that we're having a much more complicated magnetic field geometry that's harder to spot. But I'm not sure.
So yeah, any further questions from yes, David.
I think, well, first off, great talk. But just to also talk about this magnetar thing as well, we're working with a code just like this, or similar at least, and we're seeing similar growth, right? We're seeing like 10 to 17 fields sort of at the core towards the end of our simulation. So I think you're not alone in this, for sure. I think that's kind of just more of a comment that it's across all these codes that we see this growth happen.
Yeah, it's good. It's good that it's always nice to know that we're not doing something crazy, things not wrong. Yes. I think I see one from Mike.
Yep. Thanks for the good talk. I wanted to ask a question. You saw that asymmetry in the ram pressure you mentioned a little bit. Yes. I don't know how far along that was in the simulation. Do you also notice asymmetries in, like, I'm thinking like the lepton number, so like the emergence of the Lisa instability? or asymmetry.
Oh, that's interesting. I don't think I've actually looked at that. Yeah, emergence. Yeah, I haven't really looked at that. I think yeah, I really just chose things to look at because, you know, it's sort of things just from over here sort of visually reminded us of the perturbation aided mechanism. And so we started looking at that. But yeah, so I'm really not sure about this. Yeah, what's happening with the LISA instability.
Okay. Might be interesting to look at the
yeah,
you know, neutrino
definitely.
signals as well. If there's a, you know, usually if the hydro is, you know, asymmetric, maybe there might be an imprint somewhere else too.
Yeah, I think we just looked like briefly at the neutrino signals, but I think in general they looked normal. I think that they looked relatively normal, but we didn't, and because they looked very similar to the weakly magnetized case, I think we sort of didn't pursue that any much further. But yeah, that's a good point. Might be definitely worth looking into. Thank you.
Thanks.
Right, so we have time, I think, for a couple more questions if there are any. And if not, then I believe, I'm moving over to Gathertown to have a after session sort of meet and greet with the speaker. So I think if everyone's happy and they've asked all the questions that they would like to, then we can call an end to the, oh, yes, there's the link. We can call an end to this seminar. Thanks everyone for turning up, and thanks Vishnu. Can we show our appreciation to Vishnu for a great talk?
Thanks for coming, everyone.